Now recording. 12 views, you guys can get to work. The rest of us are proceeding here. Okay, so we're on to our Unit 2 review. And there's some very short questions in this review, and then there's some very much longer ones that we're going to have to deal with. We're going right back to the beginning, though. Well, the very kind of first thing we learned about was isotopes, and we essentially learned about how they come up with those average masses on the periodic table. So, like, the first thing we're going to look at here is, we'll call it average atomic mass. And I will note that the answers are right on the periodic table. So answers are on the periodic table. And again, the answers on the periodic table, it's the average molar. We didn't know about molar mass at the time. But the numbers we'll get today, and we'll just do one example, they should be like pretty close to what we get on the periodic table. They might not be exact just because of rounding, but they should be pretty close. So it's a good way you can do a question, and then you can compare your answer to what's on the periodic table, and they should be pretty close anyway. So let's say this. Let's say determine the average atomic mass of magnesium, Mg, knowing that, I'm just going to give this info in a data table here. So we'll say magnesium 24, and this 78.7% of the time. We've got magnesium 25, which is existing 10.13% of the time, and magnesium 26, existing 11.17% of the time. So those averages, those percentages should add up to 100%, or like pretty close to 100% anyway. Okay, so now hopefully you have those numbers down. I don't know if you remember back, I just sort of kind of invented my own formula. So if we're just trying to find the the mass of magnesium here, so the big, all we're going to do is we're going to take our first isotope number, which is 24, and we're going to multiply it by our first percentage, which is 78.7%, and then we'll repeat for the other ones on here. 10.13% plus 26, 11.17%. And we haven't gotten rid of the percentage, and we'll do that in our next step here. I'll just grab my calculator. You guys can do this at home too. And I'm just going to put it all together as one line. So 27 times 78.7 plus 25 times 10.13 times 26. So that should be a plus. Plus 26 times 11.17. I'm going to do all that. I got 2.47, and technically there's a percentage on that. And I mean, we could have already gotten rid of the percentage earlier, and you can if you want, but really we're just dividing by 100 here, and all that's going to do is move our decimal places 2 spots, and we get 24.32. And there's no unit on that number. It is unitless. And if you happen to look up magnesium's on the periodic table, it's 24.31, so it's almost exact, which is pretty much what we would expect there. So that's how we came up with the average atomic mass. So that would be number 1. Now there might be one of those questions on your exam. Number 2. Number 2, we can summarize. These are, again, some short questions. But it's really the boxed expression we're after here. So that's what we learned about. We learned that grams equals 1 mole equals Avogadro's number of, that's a 3, atoms or molecules. Just depends what you're talking about there. And we also should state that that X up there is the molar mass of something. So these questions I think we covered in sections 2 and 3. And remember, it's all about sort of using 2 of the 3 numbers to go ahead and solve some things. So why don't we just try a couple of examples here. And frankly, we have done sort of a lot of these throughout the course. So let's just do a couple quick ones here. Let's determine the number of molecules of NaCl in, I don't know, 4.8 moles. So this would be one of those questions where we want to write down what we're trying to find, setting it equal to what we know here. So we're trying to find the number of molecules of NaCl, knowing we have 4.8 moles of NaCl. X in a line. It's only one step, because we've got NaCl here and NaCl there. So when you have the same compound, it's just a one-stepper. Now we look to our periodic, sorry, not the periodic table, we look to our box expression, and we're after moles and molecules. So moles and molecules. So it means this question has nothing to do with grams. We don't need the molar mass. We just need to decide where that 1 mole is going to go on the top or on the bottom. And hopefully by now we are proficient in canceling and realize that that one's going to go on the bottom. Bottom. And Avogadro's number will go up top here. So 6.02 times 10 to the 23. And that would be molecules. So our question becomes 4.8 times Avogadro's number divided by 1. And I got 2.89 times 10. Don't forget the times 10 stuff. To the 24. If you didn't put that 24 in, then your answer would be off by 24 decimal places, which kind of seems like a lot. So that's maybe the first type of question that you'll come across. We've done lots comparing grams and moles. We've kind of done that endlessly here. Maybe we'll just do one more in this section. And I'll just quickly rewrite the boxed expression here. X grams equals 1 mole equals Avogadro's number. And let's tackle one more here. Let's determine the number of grams present in, I don't know, number of grams present in 5.5 times 10 to the 24 atoms of Ag. So determine the number of grams present in 5.5 times 10 to the 24 atoms of Ag. So what are we trying to find? We're trying to find the number of grams. The Eg. And what do we know? We know we have this number. .5 times 10 to the 24 atoms. And again, atoms is just because silver is a single atom, right? Eg, that's just an atom. I know I wrote molecules up here, but we all remember it's also atoms. Either or, just semantics. It's the same number, isn't it? So this question is about grams and molecules. So we can get away without the 1 mole. 1 mole is in the middle of this, but we don't really need it. So we do need to decide where we want to put Avogadro's number. And since we want it to cancel out the words, we should probably put it on the bottom. And so if we have Avogadro's number of atoms, that means we have 1 mole of silver. And then we got to look up the molar mass of silver, where it's like 107.87. You see 100 and... I lost it. I had it. I lost it. 107.87 grams of Ag. Cancel, cancel. So this one's a little more complex on our calculator. 5.5 times 10 to the 24 times 107.87 divided by Avogadro. Let's see what we get. And I'm going to do it all as one move here. And I got 985.5. Sorry, 985.5 is what I got. So I think that makes sense. I mean, silver's pretty heavy. It's over 100 for its molar mass. And this denotes that we're using a value that's, you know, at least a decimal place bigger than Avogadro. So, I don't know. I think that answer makes some good sense. So, that should cover our boxed expression questions. You'll find some of those on the upcoming exam as well. So that covers sections 1, 2, and 3. Section 4 covered a couple of different things. So let's call this number 3. And let's call this percent composition. And this was not a super difficult thing we looked at. And it was all about just determining by mass what mass each element contributes to the overall compound's mass. And I mean, we can kind of pick anyone we want here. And probably an example is the best way. So let's determine the percent comp of, I don't know, NaOH. Simple yet effective. Now, like, the first thing you're going to need to do is figure out what the molar mass of this compound is. So, you know, like sodium's what, 22.98, and oxygen's like 15.99, and hydrogen's like 1.008, and there's only one of each in these molecules, which is good. I guess we could have made this more difficult, but it's fine. Anyway, you figure out what this is, the molar mass is, and I think it's like 39.99 grams per mole. That's its molar mass. I mean, frankly, you could use 40, but we'll just go with 39.99 just to make it as accurate as we can. So if you want to get the percentage of sodium from this compound, you just take that 22.98% and you divide by the, you don't even need the percentage, frankly. It's sort of grams, right? And you take the 39.99 grams per mole, and all we're doing is multiplying by 100% here. I kind of wish I'd maybe picked a more complicated one, but we'll go with it. So 22.98 divided by 39.99 equals about 57.46. So that would be our percentage of sodium, percentage of oxygen, and there's only one oxygen, so we can just use 15.99 grams per mole and put that over 39.99 grams per mole, multiplied by 100%. And that one works out to like basically 40%, almost on the button. Again, if there were two oxygens, we would double this value up here, but we only have one. To figure out the last one, we could repeat the calculation, or we could just do some subtracting. So our percentage of hydrogen, you know, it's like 100% subtract our two answers, 57.46, and subtract 40. And let's see here. I got about 2.5%, 2.55% hydrogen. And again, these are meant to add up to 100%. So I don't care how you do that last one. And again, if there'd been more than one hydrogen, you would have multiplied there to get its molar mass. So that's percentage-wise what these things are contributing. So that sort of wasn't all we learned in Unit 4. In fact, what was kind of more interesting was taking the percentages and turning them back into a compound. So it was kind of the reverse of this stuff here. So let's call this, we'll just call it number 4. And I like to call these questions, assume 100 grams. And so they're about our empirical and molecular formulas. So just to remind you what these terms are, empirical is our lowest whole number ratio. Whole number is the key part. There's the actual formula. The empirical could be the molecular formula. That can happen, but doesn't always happen. So these are the types of questions where we've got maybe 4 steps to solving them. So I'll give you the information here. So a compound is made of, okay, 48.38% carbon, 8.12% hydrogen, and 43.5% oxygen. And I'm going to jam this in here. Determine the molecular formula knowing the molar mass is 148 grams per mole. So a compound is made of 48.38% carbon, 8.12% hydrogen, 43.5% oxygen, and with any luck, those tally up to 100%. We want to determine the molecular formula knowing that it weighs 148 grams. Now, we're going to deal with that piece of information last in step 4, so don't even worry about that. Let's not forget about step 1 here. Assume 100 grams. And we just do that to get rid of those percentages. We can now turn those percentages into masses. And then, of course, what do we do with a mass? We find the moles. So that's step 2, find moles. So just do it in order of the elements as they were seen. So we want to get the moles of carbon, and we had 48.38 grams of carbon. I almost put percent. And this is where we're using that boxed expression. This is why we didn't do an example of it earlier, because it sort of came up now with moles and grams. And this is always 1 mole here, right? So I'm going to put 1 mole on the top. And carbon weighs about that many grams. I mean, in our later lessons, we even figured out a shorter way of writing these, but, you know, we'll stick with this. So let's see, 48.38 divided by 12.01. I got about 4.02 here. So now we got to find the moles of, what's the next one here? Hydrogen. And I think we have 8.12 grams of hydrogen. X on the line. And again, 1 mole on the top. But this time it's of hydrogen. And then you look up what hydrogen weighs. And there's just 1 of them. So we get 8.12 divided by 1.008 equals 5.0 8.05s. 8.05. And lastly, on to oxygen. Mole of oxygen equals, we have 43.5 grams of O, and 1 mole of O is about 15.99, and I'm sure if you put 16 it would probably be fine as well. Uh, 43.5 divided by 15.99. Get 2.72. Okay, so we got our three answers here. And we're going to carry those on to step 3, which is divide by the lowest one. And it looks like the oxygen is going to be our lowest one, but we'll get to that. So step 3, divide. And I like to rate them like this and then put their subscript. So 4.02. We got hydrogen here, 8.05. And oxygen, 2.72. So like I said, we'll divide by the lowest one, which is that one we just came up with. So I can tell we're getting 1 oxygen here. And we got 2.95 here for hydrogen. I'm thinking that's supposed to be about 3. You know, like we know we're not supposed to round too much, but when we're at 2.9 something, I mean, it's basically 3. And carbon, 4.02 divided by 2.72 gives us 1.5. Now this is all about finding the empirical formula, which we haven't done. And remember, our empirical formula says we need whole numbers. Well, that is not a whole number, right? So all we got to do is just, well, when they're halves, it's pretty easy. Just multiply by 2, right? Double everything, and that'll give us 3 carbons, 6 hydrogens, and 2 oxygens. So now we have our empirical. This definitely seems like a lot of work for a 1-mark multiple choice, doesn't it? On a written one, this would be worth like 6 marks. Now we do have that 148 that's still kicking around. So what we got to do is we got to figure out what this thing weighs, you know, what the molar mass of this compound is. Molar mass of this thing, if you add it up, so there's 3 times, I'll just do it underneath, about 3 times 12 plus 6 times 1 plus 2 times 16. I'm trying not to be super accurate here. You get about 74 grams per mole. So this thing weighs about 74 grams per mole. And if you flash back to the question, the molar mass said that it was actually like double that, which is good, which means we're right on the right track here. So we can go into our step 4. Step 4 doesn't really have a name. It's sort of like you get the right question, or sorry, you get the right answer. But it's all about taking your molar mass, which is given in the question, molar mass, divided by your empirical mass, which is just what we figured out. So the molar mass is given in the question at 148 grams per mole. And we just determined that this thing weighed 74 grams per mole. This should always be a whole number. Can't have any half numbers here. It's a 2. And so all that means is that that formula, the empirical formula that we found earlier, we're going to double everything. So C6H12O4. And so that should have the mole of 148. That's the whole point of that. There were a few other questions we did in that section where it didn't give you percentages. I just gave you the masses. And in those questions, you know, you skip step 1 where you assume the 100 grams because you already have grams. You just kind of start at step 2 and then you can proceed. So we did some ones with compounds and we did some ones with hydrates. So you can take some time to study those up. So that was, I think that was number 4 we just worked on, which is assume 100 grams. So we're on to 5. Also happens to be section 5, which is the mole ratio. Mole ratio compares moles of 2 different substances. Comes from a balanced equation. So all you need is a balanced equation, and then we can do some mole ratio questions. Maybe I'll jump to a new slide for that in a moment. Okay, so we just need a balanced equation. Let's have NH2 plus H2 gives us 2NH3. Balance this one, 3, there we go. Haley was asking about that 74 grams. Just I'll jump back for Haley's sake. This is where I got the 74 grams from. I figured out what 3 carbons, 6 hydrogens, and 2 oxygens weighed. It weighed 74. Bam. Okay, so mole ratio. So let's do this. Let's determine the number of moles of NH3 produced when 10 moles of H2 reacts with excess N2. So we know limiting reagents is on the horizon, but this one's not a limiting reagent one because I'm just giving us one number. And if you see the word excess, that means that there isn't a limiting reagent. It's already been determined for you. So again, with this style of question, we're just after trying to find out, so let's write down what we're trying to find, which is the number of moles of NH3, and given 10 moles of H2. So we have different substances now. So number of moles of NH3, 10 moles of H2, X in a line. And so our mole ratio is going to come from a balanced equation. So there's nothing to do about N2 in this question. It's all about this 3 hydrogens and the 2 in front of the ammonia. So where do you want that 2 in front of the ammonia, top or bottom? Well, better stick to the top because we don't want it to cancel out. That means the 3 goes on the bottom for the hydrogens. Cancel, cancel. 10 times 2 divided by 3. So not quite a whole number. 6.67. So that's how many moles would be produced. Frankly, at this point, when we learned about the mole ratio, we're kind of like, yeah, so what? And I mean, it sort of did open up a whole bunch of chemistry for us because it was the first time we had a question that was comparing different substances here, right? NH3 and H2. That was different. It was still a one-stepper because it was just about moles, but then that led us into the realm of questions with 3 steps involved in them, and that got us into our limiting reagents. So we'll call this number 6. Mass to mass, or molecules. And this is where you can always grab your mole map, because these are essentially solid-to-solid questions. And again, I don't care how you do this. You can do it as 3 separate steps. I prefer to do these as 3 steps all together so I can cancel everything out. Because they're fairly repetitive. You know, it's usually the first step's about moles and grams. That second step is a mole ratio. And then the last step is about grams or molecules. I guess it depends what you're trying to find. So again, all we need is a balanced equation. How about this old classic? Balance, balance. And again, I know we have all different states here, but we can pretend maybe it's at a really cold temperature. It doesn't say. But here's what we want to do. We want to calculate the number of grams of Al produced when 100 grams of AlCl3 decomposes. So perhaps some hints that this is a 3-step question is we're after the number of grams of aluminum, and then we're given 100 grams of a different substance. So we're talking about masses here. We've got 2 different substances going on. So this is going to be 3 steps. So I like to kind of set this up ahead of time. Now, first thing I'm going to put is I'm going to put this number of grams of Al. And then I'm going to set that equal to my 100 grams of AlCl3. And then I'm going to do 3 of these. So our first step is we can take this 100 grams of AlCl3 and turn it into moles. So this would be like from our boxed expression. So 1 mole of AlCl3. Now we need to figure out the molar mass of aluminum chloride. Works out to 133.34. I'll let you guys do that on your own. And we can cancel the grams with the grams. So again, to remind you that this came from the boxed expression, moles and grams. If I stop right now, our answer would be in terms of moles of AlCl3. We don't want that. So next step is we're going to use a mole ratio. So to our question here, we've got a 2 in front of AlCl3 and also a 2 in front of the Al. So I guess it's just important to get them in the right spots. So 2 moles of AlCl3 there. Cancel, cancel. 2 moles of Al up top. Technically, your number wouldn't change at that point because it's 2 and 2, but whatever. So where did that come from? That came from the balanced equation. And then to finish this off, again, we're back to the boxed expression. And we want the moles to cancel, so I'm going to put that on the bottom. And this weighs 2698 grams. Cancel, cancel. So we should have all the numbers we need. 100 times 1 times 2 times 26.98. Divide by 133.34. Divide by 2. Divide by 1. Let's see what we get. I got 20.23. I suppose I should rationalize that answer. We started with a decomposition of 100, and so one of them's 20, the other one's probably 80. But that makes sense. Again, if I had 100 and I decomposed it and I came up with like 500, well, that wouldn't make any sense. How do I create mass from there? Can't work. Now, maybe we should try one other one here that involves molecules. I mean, we can even use the same balanced equation. So I'll jump to the next slide here in a moment. You can start writing that same balanced equation at the top. So 2AlCl3, 3Cl2 plus 2Al. Oh, I forgot all my states. Here's what I want to do. Let's calculate the number of molecules of Cl2 created when 200 grams of AlCl3 decomposes. Okay, I'll give you guys a couple of minutes to sort of tackle that one on your own. Okay, so let's do it here. So we want the molecules of Cl2, number of molecules of Cl2, knowing we have 200 grams of AlCl3. So two different substances means three different steps. So I guess we can reuse that molar mass from earlier. So we got 1 mole of AlCl3 and 133.34 grams of AlCl3. Reusing info is always good. I do it. Mole ratio. Now we're comparing here Cl and Al. So I'm going to put that 2 moles of Al on the bottom, AlCl3, and the 3 moles of Cl2 up top. Cancel, cancel. And in my last step here, 1 mole of Cl2 on the bottom. It's about molecules, right? So I better put Avogadro's number up top here. 23. So to the calculator. So 200 times 1 times 3 times 6.02 to the exponent 23 equals, divide by 133.34 equals, and divide by 2. So I got an answer of 1.35 times 10 to the 24 molecules of Cl2 that are formed. I mean, hey, that answer like make more sense if we change it into grams. That way, then we could say, oh, that's how many grams are created. But you know, that was the question. So there's a couple of longer ones. You know, and those on a written test are probably worth 6 marks. On a multiple choice test, they may be only worth 1. So you might have to, you know, bide your time smartly. And on to our last one here. Wow, limiting reagents. What number are we on? Number 7? Number 7. Limiting reagents. Is the reactant that gets used up first and stops the reaction. So when one of the reactants gets used up, the reaction stops. That's your limiting reagent. And the other one that's left over is your excess reagent. So why don't we tackle a question here? Let's see. Oh, I don't know. Hey, let's go back to now. Let's flip this one around here. So we'll go Cl2 plus Na gives us 2 NaCl. I better put a 2 in front of that. Okay, and here's the question. Let's determine the mass of NaCl created when 50 grams of Cl2 reacts with 20 grams of Na. Okay, so this one is different from the other ones because we have two masses, and we don't know which one's limiting. We don't know which one's getting used up first. So this is where we have to like forget about one and recalculate. So just, I don't know, over the years, I've come to just sort of forget about the first one. So we're going to forget about that 50 grams, and we're going to use the 20 grams and calculate how much chlorine we actually need to react perfectly with that one. So let's do that here. So like I said, we want to calculate the grams, oh man, of Cl2. Sorry, something's out of whack here. Let me try a new slide. Oh, jeez, okay. This could get sloppier than normal. So we're after the grams of Cl2, knowing we have 20 grams of Na. Sorry, it's out of alignment here. Now remember, this is just going to be sort of a fictitious calculation. This is not our final answer. And it's kind of similar to what we've done here before. So let's see. So we're after 1 mole. So 1 mole of Na is 22.98 grams of Na. Cancel, cancel. Balanced equation gives us 2 moles of Na here and 3 moles of Cl2 up top. And then lastly, 1 mole of Cl2. Now there are 2 chlorines, they're 35.54, so it's about 70.9 grams of Cl2 here. Cancel, cancel. So we're going to get an answer here in a sec, and this answer is just going to be for referencing. It's not an actual answer to our question. So you grab the old calculator, and we're going to go 20 times 1 times 3 times 70. And then we'll divide by 22.98, and then also divide by 2. And I got 92.56. Now, this number is not an answer to anything more than letting us figure out if sodium is limiting or in excess. or chlorine or whatever we're doing here. So we got to remember that the question said we actually had 50 grams. So 50 is what we have. So here's what I like to say is we need 92.56 grams. We have 50 grams. You need $92 to make a purchase. You have 50 grams. That means you are limited for making the purchase, and thus chlorine is the limiting reagent. Had we done this the other way around, we would have found that sodium was excess and chlorine was still limiting. So now we can sort of proceed on to the final step here, final thing in our review, which is actually answering the question, because remember the question said how many grams of NaCl are created when those two react, and then value I want to put here is that 50 grams that we actually have. So 50 grams of Cl2. You can put your 3 steps in. I'm just going to go ahead and do it. I guess I need the molar mass of this one first, though. And 58.44 grams. So this should give us our answer here. 50 times 1 times 2 times 58.44 divide by 70.9er. That should do it. 82.4. And again, to rationalize our answer, we started with 50 and 20, and somehow we made 84. Well, that doesn't seem to add up, does it? So what? Something has gone wrong here. I'm not sure what's gone wrong here. It seems like we've done this reasonably correct. Maybe we screwed up the limiting reagent. I don't know. I don't know. Anybody catch a mistake here? I feel like there's something wrong. The mole ratio is Cl3. Is it Cl3? It was Cl3 for the previous example, but I can't go back. It shouldn't be Cl3 for this one. Remember that it was Cl3 for the for this one here, but doing this one here, so it looks like we should have a 1. But that was a good thought anyway. We got a 2 and a 2 and a 1. I don't know what I'm not seeing what we did wrong. Everything feels like it went correctly. Maybe I'll just recheck my calculation here. Maybe I typed it in wrong. It could be a possibility. 50 times 2 times 58.44 divide by 70.9. I still get 82. Oh well. I don't know. I swear everything looks right, but I know the answer is wrong. I don't know. Anybody else awake out there? Something not right. I don't know. I swear we have done this all properly. Maybe that 92 we calculated earlier is wrong. Maybe we'll double check that. That could be, let's see, times 3 times 70.9. Divide by that. Divided by 2. No, I got the same answer there. Isn't the balance equation 2Cl, not 3Cl2? Again, it depends on the one we're using here, right? Again, that's our balanced equation. I don't know, whatever, kids. Maybe I don't know. If I hadn't rationalized my answer at the end of this question, nobody would have known it was wrong. We would have just said, yeah, 82. Yeah, that sounds good, whatever. So, I don't know. I'll keep looking at this. I can't seem to find a mistake. I feel like everything went properly. Oh, wait a minute. Now I think I see what Haley's saying. Yeah, you know what? I did screw up. I screwed up back here. You're right. I put a 3 there because I was thinking that was from the previous question. So you're right. That should be a 1. Okay, so that changes things. Let me double check that now. There we go. See, if this were in class, people would have been yelling at me when I put that 3 in the first place. But since I'm doing this online here, okay, I got 30 now. Well, let's see. That probably changes things, doesn't it? That should be 30. So now, actually, this does end up being the excess reagent because we need 30, and we have 50. So this one is excess, and then that makes Na limiting. So yeah, so this is totally wrong. And again, we wouldn't have known had we not rationalized. So we actually do need this 20 grams of Na here. And then, I mean, this rest of the thing is, well, it's all wrong. This is 1 mole of Na. That should be 22.98. And then that should be, what's that, 2 moles of Na? Yeah. Okay, I got about 50 now. That seems to make more sense. 50.8. So Haley caught that mistake. Haley, I'm going to give you a bonus mark on your exam for actually being awake and doing the question and spotting the mistake. 1 bonus mark. And I won't forget that. Okay, so there's a good teachable moment. You should always check your answers to see if they're correct, because you never know when you're going to screw it up. Okay, so yeah, I think we've been at this for an hour now. So I can let you guys go, and I'll post this review online, and maybe I'll edit out the part where I did it wrong. Yeah, I guess we'll find out. Okay, so go do that practice test, the stuff, the quizzes, all that. That would be great. Go do some studying. Some of you guys still have that quiz at the end of Unit 4 to tackle. So feel free to do that too at some point. Yeah, alrighty. Good times, good class.